How many nucleons are there, first of all? In that one and in that one. How many nucleons are in that nucleus? Mike? I'm not trying, this is not a hard question. One, just say it, yeah? There's one nucleon. How many nucleons are in that hydrogen there, though?
We know two.
How many nucleons? Why do you know there's two?
One proton. So we just subtract
One proton and
one neutron.
one neutron. Where was that neutron here?
And the helium.
But there's no helium. Where's the neutron here? Where's the neutron here?
There.
It isn't there. Now, this is one of the other processes. If we go back to the previous one where we had deuterium, that's deuterium, that's a version of hydrogen, it's just a bit heavier. Yeah? That's being made by smashing together two naturally occurring protons in a hydrogen nucleus. And we've got one of those protons turning into a neutron. That doesn't make sense, does it? What is this particle here? And if you say electron, you can just step out. No, the one before that. It's a positron. Okay? So for those of you, so where is this positron before? It wasn't there before. It's become produced through this reaction of smashing together normal hydrogens to make deuterium. So positrons aren't really that common. They have come from one of the protons turning to a neutron, releasing a positive electron, a positron, and this V. What's that V represent? Neutrino. Yeah? It is a neutrino. It's not an anti-neutrino. Now, there's two things missing here. What's missing about that neutrino here that ought to be there? How much mass? Go on. A neutrino is a particle that's associated with another lepton. Okay? So one of the things we need to build a model of is when there's a reaction, we need to keep certain rules consistent. And when we've got a nuclear reaction like this, yeah, there's three basic rules. We need to keep the same number of charges the same. So charge is conserved. We need to keep the same number of nucleons, right? So we've got 1, 1, 2, 0, and that's got no nucleons, yeah? But we also need to keep the same number of leptons. Now, a lepton is a group of is a family of subatomic particles that exist because they have to exist, yeah? They're part of the grand scheme of things. An electron is a kind of electron. A positron is its antimatter cousin. Yeah? Now, that means that when we see an electron in an equation, not anything to do with electricity, an electron in an equation, if it's a nuclear reaction, we need to also incorporate its antiparticle as well. Now, this lepton here has its own corresponding particle that's a lepton, that's a real particle. That thing there is called a neutrino. And it's an electron neutrino because there are two other types of neutrino as well. Okay. So in this example, this is positron emission from fusion. Okay, so you can describe that reaction as a fusion reaction. Right? These are leptons. One's an antiparticle, one's a particle. So we need to keep the number of particles, if you like, the same as antiparticles. Now, on this side, particle, that's got two particles in it, and that's an antiparticle. So we need to cancel out that antiparticle with it as well. Okay. So that you can describe that second example as a fusion reaction. Okay. This one, last one. Now this is where it comes, I hope, Eliza, a little bit more clearer, because that one's like that one comes if you're learning this. That one would come after this. What's going on in this third one, where we've got lanthanum 57141 turning to cerium 58141. And we've got this minus E. What's a minus E with no mass? Electron. Yeah? Beta. Yeah? So, that's a naturally occurring thing here. Right? That beta decay. There's one thing I would have thrown in here, and that would have been an anti-neutrino as well, because that also gives out gamma rays, that reaction. So for me, I would write on my one, just to make it right from what we were talking about a minute ago, Eliza, plus this anti-neutrino, that's not a good anti-neutrino, anti-neutrino there. Now, the thing I was asking there is these don't have mass or charge either. So the neutrinos don't have mass, don't have charge. They just have to be there to compensate for the arrival of a lepton. Okay? So charge is conserved, the number of baryons is conserved, and that makes sense all the time, but we also need to introduce another rule. That's lepton numbers must be conserved as well. So a lepton, and that's an antiparticle. That's a positron. That's not an I for your information. It's an IE. Okay, it's 0, 1. It's positive. That 1 becomes a minus when that's a beta particle. Okay. So these, that's a neutrino, and that's an anti-neutrino. Yeah, that's what I would have added to that. So, for the answer, three types of nuclear reaction are represented here. It says, which of these nuclear reactions represents fusion? And explain. Which one was fusion and why? The first one, don't you dare write that. I told you what to write. I told you to write fission. This one was beta. This one was fusion. Why is it fusion? And that was the answer somebody says, well, Emma.
What?
Why was that fusion? Did we lose hydrogen?
No. Did you?
Well, we went from 2 hydrogen atoms to 1. And we're losing hydrogen. Is there, how many atoms of hydrogen is there, Arthur? There's 1. So if we lost hydrogen, you could say that, yeah. It's now a heavier version of it though. Okay? So that fusion, we're going from 2 nuclei to just 1. Yeah? But that 1 is heavier. But is it exactly heavier? No, thank you for that. That's the whole point. Yeah? It's not. That fusion releases an amount of energy because the masses of that and that are not much. They're slightly less than the mass of that with that incorporated with these. Now that doesn't have mass anyway. Compared to that, it's very, very small. But the difference between this, the 2-1 hydrogen, and the 1-1 times 2 is significant. Yeah? Like you see here, look at the gradient of that graph. If you see the graph like that, the gradient is kind of steep. That should tell you the amount of energy available is a lot. That means that the masses change quite significantly going from light elements to heavier ones in the first 60 elements. Okay? Now, let's get the slide showing about the fusion. So, nuclear fusion. There's that binding energy curve that we've talked about an awful lot, yeah? Some of the elements mentioned there. It's got the number of nucleons, it goes right up to the 240, yeah? And there's examples of combinations of where this thing could turn into various things. Now, for uranium, if we were getting the bottom pair, barium and krypton, notice 92, 141, how many neutrons are going to be produced there? Can you all see that? So, 235 turning into 141 plus 92. 141 plus 92 is how much? It's 3. The last number is 3, and the last number should be 5. How many neutrons? 2, right? And the top example, strontium 94 and xenon 140. So that's 140 plus 94.
134.
And it started off at 230. So we end up, yeah? Now, strictly speaking, there's an extra neutron got to go into that for these two to be produced, right? So that would be 235 plus 1. 236, leaving 14192, yeah? The answer, the final digit is 3. That would actually mean 3 neutrons come out of this reaction for the bottom. And in this one, 140 to 94, it should be 236. That number shouldn't be 236. It should always be 235. The uranium isotope is always 235. But because we cause it to happen, we introduce another nucleon that's not mentioned here because it's forced. It's induced. So the 236 is the number we get. We follow that else? Yeah? Okay, to make the reactions for fission, yeah, we start off with the uranium-235 nucleus. We need to introduce into it, to make it unstable, a extra neutron. So we fire a neutron. So that 236, that's the nucleon number, yeah, or the baryon number. We make it 236 now. Then it's unstable. So the isotope's 235, yeah?
Yes, but you mean after fusion and fission?
Before fusion, right, we introduced, you saw the reaction before, we had one neutron going into something. Right, so that one neutron adds an extra nucleon to this. So the 235 is that the nucleus we start with, but you add a neutron to it, make it unstable, and you get these two out, or you might get these two out, depending on the energy of that neutron. Okay. So that number always goes up by 1 because you induce it. So 236 is the final number. That means in this example, that underneath the barium and krypton outcome, 3 neutrons are made, and the xenon strontium gives us 2 neutrons. Yeah? Do we follow that? But we've got to take the uranium and add the extra 1 nucleon number to it. Okay? Now, you could see that it says earlier there isn't a whole lot of difference in energy from what we started to what we end with. Yeah, so you need a significant. But again, that, remember, is per nucleon. This number, per nucleon. So if we were to draw it as just the binding energy change, that would still be massive, right? That would be a way, way up. This curve would just basically rocket up, but not as steeply as this at the beginning. So in the energy release of this, there's the neutrino, there's the example here, we're getting out that amount of energy, yeah? Notice masses in U, unified atomic mass unit, so like the average mass of a nucleon. Right, that's what that is, the average mass of a nucleon. And 16.89 mega electron volts. Is it worth remembering that? No. You'd be given it, or you'd be expected to calculate it. How is it calculated? How do we come up with that? How does that answer arrive at us?